Anatomy of the atom. Looking for patterns in chemical reactivity. Atoms of different elements differ in number of subatomic particles. This difference in atomic structure affects their chemical properties. So we know that the periodic table has been organized in a way where they have similar properties if you look within a group or you look within a chemical family. So one of the chemical families that we've looked at was something like alkali metals, right? Group 1. Or alkaline earth metals are group 2, and they all have very many similar characteristics, very similar chemical properties. Now, a few patterns and trends that you can observe in the periodic table. We've already talked that the periodic table arranges elements into periods, which are the horizontal rows, and groups, which are the vertical columns. And as we said, we're not going to refer to them as rows or columns. We might say it, I might say it accidentally, but in fact, I want you using the terms periods and groups. Now, I introduced you guys to the aluminum staircase in the previous chapter, and we talked that the aluminum staircase separates the elements into your metals and your non-metals, and that the groups bordering this staircase or ladder exhibit some metallic and non-metallic properties, which we call our metalloids. And these are the ones that pretty much lie along the borders of the aluminum staircase or the aluminum ladder, whichever way you want to use to refer to it. So here's our periodic table. Okay, here is the aluminum ladder. Right. So metals, non-metals. Okay. Let me write down non-metals. Okay, and metals. Notice how the majority are metals. Notice these green ones here. Okay, these are the metalloids, and these are the ones that we've talked about that exhibit similar properties to both metals and non-metals. Another thing also, just to remind you guys, these numbers here on the side, the 1, the 2, the 3 here, these are the periods. Okay, so period number 1 is the first row. Period number 2 are all the elements in the second row. Period number 3 are all the elements in the third row, and so on and so on. And notice how there are 7 periods or 7 rows in the periodic table. The numbers here up at the top, 1, 2, you'll notice we've got 3, 4, all the way here, 13, 14, 15, 16, 17, and the last group number 18. Right? So the numbers up at the top are the group numbers, 1 through 18. Sometimes you'll see them in Roman numerals, and in Roman numerals, they're numbered from 1 to 8. Sometimes you might see it as numbered 1 to 8A or 1 to 8B. Okay, but for argument's sake, what we are going to do, we are going to refer to them as groups numbers 1 to 18. Okay, so we're going to look at each column as groups from 1 to 18. And we mentioned also that in these groups, right, you've got some specific chemical families, right? Group number 1, group number 1, as we said, with the exclusion of hydrogen, are the alkali metals. Group 2 here are the alkaline earth metals. And if we move across, we've got our halogens, and group 18 here are the noble gases. Now, with the other groups here, we mentioned some of them aren't given, right? Just those were given some special families, chemical family names. But if we look at, let's say, group 14, we can treat it and name it based on the very first atom that lies in that group on the periodic table. So carbon is the first atom in this group number 14. So we can call this the carbon group. The next one, nitrogen, is the first one, so we can call that the nitrogen group. Group 16, we can refer to it as the oxygen group. But keep in mind that groups 1, groups 2, groups 17, and 18 all have special chemical family names. Let's look at the anatomy of the atom and actually break down. So we know the atom is the smallest possible particle, any particle found in any compound. But we know that the atom can be broken down into subatomic particles. And we've talked about the scientists who were involved with pretty much the discovery of these different parts. So let's look at the first part. Really important part. Rutherford discovered that there was a nucleus, okay, which is the center of the atom. We know that it takes up very little space, that the majority of the space is actually with the electron cloud that are around it. Now, circling around the nucleus are what we call orbitals and shells. Now, keep in mind that when you study chemistry at the senior level, this is incorrect, right? We are looking, when we refer to them as orbitals and shells, we are referring to them using the Bohr or Bohr-Rutherford model, okay, or diagram, where we draw it as such. Next, in the nucleus, we've been able to find that there are protons. And here in this example, we are going to write down 11 protons for this example. Okay, now, if we look at that and we remember the number of protons, right, the number of protons, if we have the number 11 protons, or 11p, you might see it in a certain textbook or your notes, that represents the atomic number. So the atomic number and the number of protons are the same. So if we have 11 protons, we are referring to the atomic number 11. So if you look at the periodic table, which element in the periodic table has the atomic number 11? And you'll find out that the symbol is Na, and we are referring to sodium. So if we look at sodium, we can calculate the number of neutrons. And I haven't really talked about calculating the number of neutrons before, but we know that within the nucleus there are protons and neutrons. We know that the nucleus contains the entire, pretty much nearly all the mass, 99.9% of the mass of the atom. So how do we get that number? So to get the number 12 neutrons, what we want to do is we want to take the atomic mass of sodium. And the atomic mass of sodium is 22.99. And when we're doing this calculation, okay, whenever we're calculating the number of neutrons, and I'm going to repeat this again when I show you guys the proper equation, you want to round it off to the nearest whole number. So 22.9 is going to become 23. And remember that the atomic mass units is AMU, as we've talked about in the previous chapter. So, but units aren't going to really come into play for this part of the calculation. So what we do is we're going to take the atomic mass and we're going to subtract it by the atomic number. The atomic number is 11. So 23 minus 11 equals to 12. And that calculation helps us calculate the number of neutrons. So that's where we got the number 12. So what you do is you take the atomic mass, subtract it by the atomic number to give you the number of neutrons. Now, because we're going to refer to sodium as a neutral atom, okay? It's a neutral atom, so because we're going to refer to it as a neutral atom, there is going to be no charge, okay, no ion charge reflective in this atom. So, which means if it's neutral, no charge, if I have 11 protons, I will also have 11 electrons. Now, how do I draw these electrons? As I've said also in the previous lesson, right, as I've said in the previous lesson, that the number of electrons, right, can be drawn as such. In the first shell, right, no more than 2 electrons. In the second shell, no more than 8 electrons. Third shell, 8 electrons. And for argument's sake, we're not really going to go to the fourth shell. We are going to go to the fourth shell for some of the activities that I have, but you are not filling in more than 2. Okay, and that's where things get a little bit weird. But we are going to draw diagrams as such, right? We're going to draw diagrams as such only for the first 20 elements of the periodic table. Okay, so now, how does this work? So in the first shell, we can fit only 2. But we must fill in all the inner shells first before we move on. So before I move on to shell number 2, I must have my first shell filled. Before I move on to my third shell, I must have my first and second filled before I can go to my third. So I know I got to fill in 2 electrons in the first shell, right? My second shell, if I fill in all 8, I'll have a total of 10, which means that we're going to have one more shell on the 8th, in that third shell for me to fill in. Okay, so let's look at the electrons when we're drawing them. So first shell, 1, 2 electrons. Sometimes you may see them paired up, right? I like to keep them apart until I draw more than 4 electrons, and you're going to see it in just a second. So we've filled in our first shell. I cannot fit in any more. So my third electron, so I've drawn in my 1 electron number 2. For me to draw my electron number 3, I must do it on the next shell. So let's look at it. 1, 2, 3, 4, 5, 6, 7, 8. Notice how when I labeled it, when I drew them in, I first drew one in at each. Let's say you could say at each, let's say, hash mark for treating it like an X or like a plus sign, right? So 1 electron here, then another one here, then another one here, then another one here. Then we pair it up once we get to number 4. We get to electron number 5. So we labeled in 1, 2, 3, 4, 5, 6, then 7, okay, electron 8, electron 9, electron 10. I have filled in now 8 more electrons, right? So I cannot fit more than 8 in the second shell. So I cannot fit in another one in here. I'm already full. So where does it go? It goes on the third shell, or third orbital. There it is. And here is the name that we talked about in the previous lesson, valence electron. Valence electrons are the electrons found on the last or on the outermost shell or outermost orbital. Right? So the outermost orbital is orbital number 3. There is no orbital 4 in this diagram because we are going up to a maximum of 3. Now, look at sodium on the periodic table. So now you should be referring to the periodic table. Look at sodium. What is the period number? Okay, so what is the period number of sodium? So if you look at it, the period, okay, which are the rows, right? But we're not going to refer to them as rows. The period number that sodium belongs to is period number 3. The period number tells us how many orbitals or shells we have. So because the element is in period number 3, we are going to fill in 1, 2, 3 shells. So because of that, we can automatically fill in 1 and 2 and put in there 2 electrons and 8 electrons on the second shell and then put that 1. Now, what group number, right? So now, let's look at the group number that sodium belongs to. So sodium belongs to group number 1. So because it belongs in group number 1, it has 1 valence electron. And this is the little hint that I was telling you guys about in the previous chapter on the periodic table. So, period number, which are your rows, tells us the number of orbitals, okay, or shells, using, of course, the Bohr-Rutherford model, right? Not on a quantum level. And the group number tells us the number of valence electrons. And the group are the columns. Okay, so we've got the columns. So the group number tells us the number of valence electrons, with a certain exception, of course. And we're going to talk about the exception to the group number theory that we're going to use, or a group number hint trick that I like to use. So, let's just recap the three main subatomic particles. A proton is a positively charged particle forming part of the nucleus of an atom, right? We've drawn that. A neutron is a particle carrying no electric charge and forming part of the nucleus of an atom. And lastly, an electron is a negatively charged particle found orbiting the nucleus of an atom. So, let's look back at the diagram. This diagram, because we have labeled the nucleus with the number of protons and the number of neutrons together, this is what we call a Bohr-Rutherford diagram. So be careful if you're asked to draw a Bohr-Rutherford diagram. Bohr said that these electrons orbit at certain energy levels. We've talked about this before. The orbitals, shells, represent energy levels. So Niels Bohr said electrons circle around with energy levels. It was Rutherford who said there are protons in the nucleus. And one person that, we could still include, but it was one of his students, right, was Chadwick, who said that there were neutrons as well in the nucleus of the atom. So in fact, we could say that it's a Bohr-Rutherford-Chadwick diagram, but I guess because Chadwick studied under Rutherford, they referred to this as a Bohr-Rutherford diagram. Not to be mistaken with what we are going to call the Bohr diagram. And the difference with a Bohr diagram is, in the nucleus, we are not going to label this information. Instead, for a Bohr diagram, we are just going to label it with the symbol Na. Maybe I should have used it. Let's see. Right, we name it, or we label it with just the symbol. We do not put the number of protons. We can do that all on the outside if we wish. Right? But in a Bohr diagram, okay? So in a Bohr diagram, we label it just with the symbol. In a Bohr-Rutherford diagram, we actually place the number of protons and neutrons. So be wary of that, or be careful of that as well. So, hints in the periodic table. As we've said, the atomic number tells us the number of protons. It also tells us the number of electrons of a neutral atom has, So, let's look at a simplified diagram of the first 20, or you're responsible for the first 20, but this rule applies for all of them, not just for the first 20. So, I'm going to repeat. This rule that I'm showing you right now, the atomic number rule, applies to all the atoms of the elements of the periodic table. So, the atomic number here, let's look at oxygen. 8 is the atomic number, right? Because the atomic number are the numbers that go in sequential order. See, 1, 2, 3, 4, 5, that, and so on, so on. So, the atomic number of oxygen is 8. The atomic number, as I said, tells us the number of protons. So, if the atomic number is 8, we have 8 protons in the nucleus. If the atom is neutral, we've not created an ion. It's an oxygen atom. Right? Atoms have no charge. An oxygen ion carries a charge, as we've talked about in the previous chapter, the difference between an ion and an atom, and we're going to talk about that at the later on. So, in an oxygen atom, we are referring to a neutral atom. So neutral meaning no charge. So if we have 8 positives, how do we get no charge? We make sure that we have 8 negatives circling around in the orbitals, in the shells surrounding, in the energy levels around the nucleus of oxygen. Let's look at another example here. We look at magnesium, right? Magnesium has the atomic number 12, which means it has 12 protons, and if it's a neutral magnesium atom, it will also have 12 electrons surrounding its nucleus. So, some more hints of the periodic table. The number of neutrons is equal to the atomic mass subtracted by the atomic number. So, we have the atomic number, we have the atomic mass. Whenever we're doing this calculation for the atomic mass, round to the nearest whole number. So, with this example, 55.85, the nearest whole number is 56. And this represents, remember as we said, AMU, atomic mass units. So, that's the atomic mass. We subtract it by the atomic number, which is 26, which will give us 30 neutrons. Okay, notice that the number of neutrons may or may not match with the atomic number. So, notice where the mass is coming from for iron. It comes from the protons, right, which is the atomic mass, and with the number of neutrons. Because if we go backwards, right, we've got, as we calculate, right, 56 subtracted by 26 gave us 30 neutrons. Now, if I have 30 neutrons in the nucleus, I add it to the 26 protons, or P, that I have, right? It'll make up the mass of iron, which is 56 atomic mass units. So notice how the mass of an atom is found with the number of neutrons and the number of protons found in the nucleus. So the entire mass of any atom is found in the nucleus. Okay? I can't repeat that enough. Now, some more hints. Group number, as I told you guys, tells us the number of valence electrons, and this works primarily for the first 20 elements. So, we've got the entire periodic table here. So, let's look at the first 20 elements, because this rule is going to apply greatly for the first 20, and that's all I'm expecting. You're going to be responsible for. So let's look at the first 20, and notice how the group numbers are numbered. 1, 2, right? Look at the gap here. This gap here has what we call the transition metals. We'll worry about that next year. Okay, so we've got the transition metals, and then we jump over across to the next part of the gap at 13, 14, 15, 16, 17, and 18. Group number tells us the number of valence electrons. Valence electrons are the electrons found on the outermost shell or energy level or orbital, whatever you want to call it. Right? So, if we're group 1, 1 valence electron. If we're group 2, 2 valence electrons. But now we're going to move across. Does that mean that if we have if the group number is 13, we have 13 valence electrons? Remember, the most valence electrons that we can ever have, the most we can ever have is equal to 8. Right? So what do we do for this? Well, instead of 13, we're going to take away the 1 and treat that as the number of valence electrons. So 13 has 3 valence electrons. 14 has 4 valence electrons. 15 has 5 valence electrons. 16, 6, you can almost get the picture here, right? 17 has 7 valence electrons, and group 18 has 8 valence electrons, with the exception of helium. Helium is the only one that will have 2 valence electrons, right? Because remember, as we're going to show you guys in the next group, right? The period number 1, 2, 3, 4 that we have here. This, as I'm going to show you in the next slide, represents the number of shells. So if we're here's helium. We're on the first shell. We can only fit 2 electrons. We cannot fit 8. So 2 acts the same way for helium as 8 would for neon, as 8 would with argon. So, as I just said, the period number tells us the number of orbitals circling the nucleus of the atom. And again, this we're looking at in terms of the first 20. Okay, so for the first 20 elements. Okay, so let's look at the first 20 elements. So, we've got period number 1, 1 shell. Right? Period number 2, a second shell. Period number 3, a third shell. Period number 4, a fourth shell. Right? So, the first shell can fit how many electrons? We've said. First one can only fit 2. Why? Because we've only have 2 atoms in the first shell, or that have only 1 shell. Now, these on the second shell will have their first shell filled. But we have it to 1, 2, 3, 4, 5, 6, 7, 8 electrons. So therefore, we can actually fit up to 8 electrons on the second shell, or second orbital, or second energy level. Okay, so 2 on the first. As we said, we can fit also 8 electrons on the third. And because we are only going up to the first 20, we're only going to put 2 more on the fourth shell. We're not going to fill anything beyond that when referring to a Bohr, Rutherford, or a Bohr diagram. Okay? So for those who are looking at it at a quantum level, this rule, ignore it because you guys are referring to S, P, D, and F orbitals.